Welcome back to this second lecture on functions. In this third segment, we're going to introduce a new family of functions called logarithmic functions. Now remember that when b is a real number that's greater than 1, the exponential function b to the power x is a strictly increasing function, and therefore it's also an injective function, as we discussed in a previous segment. Now it turns out the exponential function b to the power x is actually a bijection from the set of real numbers to the set of positive real numbers. So since the exponential function is bijection, it's actually invertible, which means it has an inverse. And the inverse of the exponential function is the logarithmic function. So let b be a real number greater than 1, and let the domain of the logarithmic function be the positive real numbers, and their codomain be the set of real numbers. By definition, the logarithmic function to the base b, denoted by this symbol that is read log base b of x, is the function that takes as input an x and returns the power of b that is equal to x. Now let's illustrate this definition with an example. Let's pick a particular value for the base b, say 2. So we're going to compute the logarithm base 2 of x, where x ranges over all of these values. Now these are powers of 2 just to make our computations easier. So the second row is going to contain the log base 2 of x. What is the log base 2 of 0? So what is the power of 2 that is equal to 0? Actually, there's no such number. 2 power anything is never equal to 0. That's why the function that we're discussing here, the logarithmic functions, are defined on the set of positive real numbers, not including 0. Therefore, the function is not defined at 0. Now let's consider x equals 1. What is the logarithm base 2 of 1? In other words, which power of 2 is equal to 1? Well, 2 power 0 is equal to 1, therefore the log base 2 of 1 is 0. Which power of 2 is equal to 2? Well, the answer is 1. 2 to the power 1 is 2, so the log base 2 of 2 is 1. Which power of 2 is equal to 4? Well, 2 squared is 4, so the log base 2 of 4 is 2. Similarly, 2 power 3 is 8, so the log base 2 of 8 is 3. Log base 2 of 16 is 4, and so on and so forth. So I'll let you compute the remaining 2 values by finding the powers of 2 that are equal to 128 first, and then 1024. You got it? The answers are 7 and 10. Now, let's draw the graph of the logarithmic function for base b equals 2. Here is my graph paper. I position the y-axis all the way to the left. Since the domain of the logarithmic function is the positive real numbers, I'm not going to need any space on the left of the y-axis. Let me position the x-axis over here, which thereby defines the 0 on the y-axis. The numbers on the y-axis go up this way and they decrease on the way down. Now, I'm going to position the ticks on the x-axis one by one. And in order to draw the graph in a way that makes it somewhat visible, I'm going to assume that each square here is approximately 10 units on the x-axis. So the first tick for x equals 1 is right there next to the y-axis. And the value of log base 2 of 1 is 0, so here is the first point. For x equals 2, the value of the log base 2 is 1, so here is the second point. And I'm going to go through the values in this table and draw the corresponding points plus 1 or 2 others. So for x equals 4, the log base 2 is equal to 2. x equals 8. The log base 2 is 3. Let me continue with 16. The log base 2 of 16 is 4. Then I'm going to go to 32, even though it's not in the table. It's the next power of 2. Log base 2 of 32 is 5. Log base 2 of 64 is 6. And log base 2 of 128, which is approximately past the right-hand side of the arrow here, is equal to 7. So this is the graph for the log base 2 of x, although I only put the points corresponding to some of the integer values. Now, the first thing to notice is that this function is strictly increasing, but it's increasing very slowly. In fact, if you look at the table, you notice that every time the value of the input x is multiplied by 2, as happens here in the first few columns, when the input is multiplied by 2, the log base 2 only increases by 1, which is why when you get to relatively large values of x, like 1024, the log base 2 is only up to 10. So it's a very slowly growing or increasing function. Just to give you a comparison, let me draw the straight line for the identity function. F of n equals n. And here it is in this graph. Notice the logarithmic function grows a lot slower than even the identity function, which in itself grows a lot slower than x squared, or even more so the exponential functions. Since a lot of people have trouble with the logarithmic functions, let me give you a couple different ways of thinking about them. The first one has to do with what I mentioned before. Every time you multiply the value of x by 2, you're adding 1 to the logarithm, base 2. So another way to look at the logarithm of, say, 128 is the number of times you need to divide 128 by 2 until you reach 1. And the answer is 7 times. So for example, the number of times you need to divide 16 by 2 to reach 1 is 4. Let's do it. If you divide 16 by 2, again by 2, again by 2, again by 2, you do it 4 times, and that's the value of the logarithm. Of course, if you ask the value of the logarithm of a number between 8 and 16, then its value is going to be a real number between 3 and 4. So that's the first way to think about the logarithm, the number of times you need to divide the number by 2 until you reach 1. Another way I want you to think about it is to remember that the logarithmic function is the inverse of the exponential function. So let me illustrate this here. First, let me write the exponential function. So 2 to the power of y is equal to x. In other words, y is the input to the logarithmic function, and x is its output. It's 2 to the power y. Now, what would be the inverse of the logarithmic function? Well, you would feed it x, and it would return y. It goes in the other direction. So in other words, the logarithm base 2 of x, that's the input to the logarithm, is equal to y. Notice here you go from y to x in the exponential function. Here you go from x to y. Now why does this work? Well, what's the logarithm base 2 of x? Since x is equal to this number, logarithm base 2 of x is logarithm base 2 of this number. And what's the logarithm base 2 of this? It's the power of 2 that's equal to this. Well, the answer is y, since 2 to the power y is equal to 2 to the power y. And here is the visualization, if you wish, of the fact that the logarithmic function is the inverse of the exponential function. Actually, here is even a better visualization, I think. Let's use the graph of the function. Let's say you want to compute the logarithm base 2 of 16. You would start at the origin, you would move along the x-axis until you find 16, and then you will move up until you hit the curve or the graph for log base 2, and you would read the answer back out on the y-axis. So the log base 2 of 16 is 4. Similarly, the log base 2 of 32 would be computed like this. You find 32 on the x-axis, you move up until you hit the graph for the log base 2, and then you read out the answer on the y-axis, and that's 5, the log base 2 of 32. Well, since the logarithm is the inverse of the exponential function, let's do the opposite computation and see how it works. So suppose I want to compute 2 power 4. I would actually start at the origin, and now I'm going to go in the other direction. I'm going to go up until I reach 4, then I move to the right until I hit the graph for the log base 2 function, and I would read out the answer on the x-axis. And this number, remember, is 16, and indeed 2 to the power 4 is 16. Let's do a second example. Say I want to compute 2 to the power 5. Let's start from the origin. I would go up the y-axis again until I hit 5, move to the right until I hit the graph for logarithm, and look the answer straight down on the x-axis. 2 power 5 is 32. You see, because the logarithm and the exponential functions are inverses, in one case you go from the x-axis to the y-axis, that's the log base 2 function. In the other case, you go from the y-axis to the x-axis. The same curve can be used to compute both functions because they are inverses of each other. Now, to emphasize this point, let me remind you that the exponential function is defined from the set R to the set R plus, and since the logarithmic function is the inverse of the exponential function, it is defined the other way around, from the set R plus, the positive real numbers, to the set of real numbers. So everything makes sense. Now, let me make another point about the logarithmic function. First, let me draw again the graph of the function for b equals 2. So we already have those points. Now the next thing I want to do is what happens when the input x is smaller than 1. In other words, between 0 and 1. So let's say x is 1/2. What is the power of 2 that's equal to 1/2? Well, the answer is -1, because 1 over 2 is 2 power 1/2. So actually the graph continues to the left of 1 with this point. And let's do one more value. How about x is 1/4, a fourth? What power of 2 is equal to 1/4? Well, the answer is -2. So here is one more point. So here is the complete graph for the log base 2 of x. Notice as x goes towards 0, the logarithm base 2 goes towards -infinity. Now for comparison, let me put the graph of the identity function to confirm that log base 2 of x grows or increases a lot slower than even the identity function. But the next point I want to bring up is that the base doesn't have to be equal to 2. So what happens if we increase the base to, say, 3? What is log base 3 of x? Well, for x is equal to 1, log base 3 of 1 is 0 because 3 power 0 is 1. So the graph for log base 3 of x is also going to go through this point. Now what would be the next easiest point to compute? It would be for x equals 3. What is the power of 3 that is equal to 3? Well, the answer is 1. So the next point here for the graph of log base 3 of x will be here. And you see that the graph for log base 3 of x is also strictly increasing, but it actually increases slower than log base 2 of x. So make sure you understand this important point. Log base 3 of x is less than log base 2 of x when x is greater than or equal to 1. Think about it. If you start with the number x and you ask yourself how many times do you need to divide that number by 2 until you reach 1? Well, if you ask a similar question, how many times do you need to divide the number by 3 to reach 1, that number will be smaller than in the first case. So, the larger the base of the logarithm, the slower the increase of the logarithm when x is greater than 1. Now, the effect is reversed when x is smaller than 1. So, for example, what is the logarithm base 3 of 1/3? Well, 1/3 is 3 to the power minus 1. So the logarithm base 3 of 1/3 is minus 1. And therefore, the graph for log base 3 of x between 0 and 1 is actually higher up than the graph for log base 2 of x. But typically, we're interested in values of x that are 1 or usually larger. So this is the pattern that you need to remember. In other words, the larger the base of the logarithm, the smaller the value of the log base b of x. Now let's briefly discuss a theorem pertaining to logarithmic functions. This is the third theorem in this lecture. Let's assume that b is a possible base for a logarithm, namely it's a real number greater than 1. Let a be another possible base for the logarithmic function. Let x and y be positive real numbers so that you can feed both x and y to the logarithmic function. The first statement of the theorem says that the logarithm base b of the product x times y is equal to the addition of the respective logarithms base b of x and y. So the important thing about logarithms, why they're so useful in computations, is that they convert products to additions. The second statement of the theorem says that the logarithm base b of x to the power y is equal to y times the logarithm base b of x. Now that basically follows from the first statement, because x to the power y is nothing but x times x times x y times. So it's a product which gets converted to an addition. So if you have the product of x y times, you're going to get log base b of x plus log base b of x plus dot 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 y times. In other words, you're going to have y times log base b of x. And finally, the third part of the theorem states that the log base a of x is equal to this fraction. Now, the reason this is important is because it allows you to convert from one base, namely base b, to another base, base a. Now, why would that be useful? Well, for example, on some calculators, you don't have the logarithm base 2 available. You only have logarithm base 10. So what if you want to compute logarithm base 2 of 100? So a is equal to 2, but the one you really have a key for on your calculator is the log base 10. So you can set b to 10 and then use the formula, and now you can go ahead and compute log base 10 of 100. Well, this one you can do in your head. What's the power of 10 that's equal 100? That's 2. And now you can use a calculator to compute log base 10 of 2. When you do it, the answer you get is approximately 6.64. And notice that makes sense because 2 to the power 6 is 64, 2 to the power 7 is 128, and 100 is between 64 and 128. And therefore, this answer is quite plausible because it falls between 6 and 7. Now let me conclude this segment with an important reminder. What is b to the power log base b of x? Well, the answer, I hope you can figure it out now, is x. Now, why is that? Well, let's say you start from x, and then you apply the logarithm function to it. You get some number, to which you then apply the exponential function base b to get some other number. And the question is, what is that number? Well, the one thing to remember is that the exponential function is the inverse of the logarithmic function and vice versa. So when you start from x, you first apply the log or the logarithmic function, and then to that number you apply the inverse function. What you're getting is you're getting x back. And that's why this equality holds. Similarly, if you go in the other direction, you take the log base b of b to the power x, you should also get x back. Let's check that a different way using the theorem above. In particular, let's use this result here. Log base b of b to the power x is going to be equal to x times log base b of b, and sure enough, log base b of b is 1, x times 1 is x, so you're getting x back. But you don't really have to do all these computations. You should just realize that if you start from x and you first apply the exponential function, you get some number. But then when you apply the inverse function, the logarithmic function, you should get x back.